Alright, welcome back to the third video. I'm going over the practice problems for our exam 3 in Math 161 class. I'm going to go over 11 through, I'm thinking number 16, 11 through 16 in this video, okay? Alrighty, number 11 and 12 are writing inverse functions and writing the domain and range of the function and its inverse. So let's write the inverse function for this f of x first. Let me rewrite f of x as y equals 7x plus 1 over x plus 2 so that I can switch the x and y. Okay, that's how you write the inverse function, right? So write down x equals 7y plus 1 over y plus 2. We're solving this for y. And remember, we multiply both sides by the denominator of y plus 2 first. Then I will have xy plus 2x, oopsies, equals 7y plus 1. Now, why are we doing this? We're trying to solve for y. So what I'm going to do is I'm going to highlight every term that has y in it. This one has y in it. This doesn't have y. This has y in it. Now, all the terms that has y are highlighted in yellow. All the terms that doesn't have y are highlighted in green. I'm going to gather the same type or the like terms, I will say, to the left side. xy minus 7y equals, I'm going to have 1 minus 2x. So the green thingies are on the right. The yellows are on the left. And the yellows got moved to the left. Why? Because they both have y. That I can pull out the y to the front and write it as x minus 7. And the numerator, on the right side is 1 minus 2x. When you're doing this moving, or, well, the inverse operation to make the term appear on the other side, make sure you are switching the signs though, okay? Now, what's the very last step? Divide both sides by x minus 7. Remember, guys, I'm going over this kind of quickly because you've seen this before. You've seen this before. But if you want to look at the resources where I go over this in a much slower pace, this is from section 3.1 when we first talked about inverse functions. So you can watch the videos on that. But f inverse of x, using that inverse notation, is 1 minus 2x divided by x minus 7. So that's what you're going to circle for your inverse function. Now let's talk about the domain and range of this, of both functions. So first, they want you to write the domain and range of f in inverse notation. Now take a look at this function. Notice that we have x plus 2 in the denominator. So the domain is x cannot be equal to negative 2. Why do I say that? Because when x is negative 2, what happened to the denominator? It's going to give you 0, right? So x cannot be equal to negative 2, and that is the domain of f. That's the domain of f, right? So let's write that in interval notation. From negative infinity to negative 2, union negative 2 to positive infinity. We use the parenthesis. Do not use a square bracket because square bracket means you're going to include the value negative 2. Now listen though, the domain of f is going to be the same thing as range of f inverse. So you can copy the same answer down in the range blank for the inverse function. And the method that we learned in unit previous unit is taking the horizontal asymptote. Remember, the horizontal asymptote, when the degrees of the numerator and the denominators are the same, is going to be when y is equal to the ratio of the leading coefficient. So you do get the horizontal asymptote to be y equals negative 2. And we can algebraically show that by setting this function equal to negative 2, that it will never be equal to negative 2. That's why it's going to skip it. But it's much easier to just find the domain of the original function and call that the range of the inverse function instead of bringing this horizontal asymptote concept into it. Not that you don't know how to do it. You do know how to do it. But now let's go and find the range of f. Like I said, finding the range, you will have to use the horizontal asymptote and show that it's not going to cross that horizontal asymptote. But what I can do is this. I can go ahead and find the domain of f inverse. I'm about to find the domain of f inverse and just say that's going to be the same thing as the range of f. So take a look. Look at the denominator, it's x minus 7. We know that cannot be equal to 0 because we're not allowed to have 0 in the bottom of a fraction. Add 7 to both sides. What we get, what we get is x cannot be equal to 7. And this is the domain of f inverse. So let's write that down in interval notation. from negative infinity to 7, union 7 to infinity. And now, this is the domain of f inverse, which means this is the range of the original function f. So you copy that the same over here. That's how you will find the domain and range of a rational function and its inverse function, okay? All right, let's look at something similar, but this one was straight out of this unit, really. Log function. Let's go ahead and write the inverse function first and then do the domain and range. First write this as y equals log. Now, real quick, what's the base here? Base is 10, right? The base is 10, and I wrote it over there because you will need to know what the base is when you rewrite this in an exponential form. Subtract 5 from both sides, you get y minus 5 equals log base 10 of x minus 3. You know that you're not allowed to add 3 yet, and this is where we're going to rewrite this in an exponential form. Exponential form has a base of what? 10, and the exponent is x minus 3, and that equals y minus 5 over there. So y minus 5 equals 10 to the x minus third power. If you add 5 to both sides, you get x 10 to the x minus third power plus 5 is y. Therefore, g inverse of x equals 10 to the x minus third power plus 5. That's how you will find the inverse function of a common log function. Okay, so let's talk about the domain and range of this. First, the domain and range of g. Notice, this is a logarithmic function, right? For a log function, argument must be greater than 0. And we talked about that in our previous video on number 8, A and B. So argument must be greater than 0. So what we're going to do is we're going to solve this for it. Argument is what? X minus 3. X minus 3 must be greater than 0. That means x must be greater than 0, and that is the domain of g. Let's write that down in interval notation. So if it's greater than 3, you know, back when we first started, I always graphed every single one of my inequalities, right? To convert it into interval notation. But I think everybody's at a point we can just go straight from this inequality to interval notation. If it's greater than 3, where is it going? It's getting bigger, 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 bigger. So it's going to positive infinity. Now, if I know the domain of g, guess what I also know? I know the range of g inverse. That's the same thing as the range of g inverse, 3 to positive infinity. Now, look, you remember exponential function. Exponential function. The domain of an exponential function is always all real. Domain of g inverse, which is an exponential function, is all real. Why? Because there's no restriction on what number can be considered to be an exponent or power. We can raise something to any power if we want. So, domain is going to be negative infinity to positive infinity for the g inverse, which tells us the range of our logarithmic function is going to be all real. All right, that's it for number 11 and 12. Just kind of talking about the idea that domain of an original is equal to the range of its inverse and the other way around. And I have both types, one rational and one logarithmic functions on your exam, okay? And I know Alex will create random problems and you will have, hopefully you will see, yes you will, because I did set it up that way. Alrighty, number 13 through 16 are properties of log, and I actually love number 15 and 16. Got them from Alex, because I think some of the online calculators, if you type this in, they will do it for you. And what's the fun in it, right? I want you to actually try to do this yourself. So let's go over 13 through 16, and we'll take another quick break, okay? All right, number 13, write the logarithmic expression as a single logarithm with coefficient 1 and simplify as much as possible. Now, this is from what, section 3.4, and you guys did a short Canvas quiz for this one. So if you missed this lesson, please go through that first. Alrighty, I'm going to go ahead and rewrite these, but first I'm noticing these coefficients in front of them. Let me send them right back up to the exponents, okay? So it will turn into log base 5, k to the 1/2 power, minus log base 5, m to the 1/3 power, plus log base 5, x to the what power? 2nd power. All right, thank goodness they all have common log base 5. So I can put them in a single log, right? So log base 5. Now, k to the 1/2 power has a positive, positive sign in front of it, right? So that one stays on top. But remember, when you are subtracting these common base logs, that turn into a division, right? So I'm going to go ahead and put m to the 1/3 in the denominator, right? So because it had a minus symbol right there, that's why it's in the bottom of the fraction. Now, be careful though. Now this one is a very common mistake. People put that in the bottom with this m guy. No, this one has a positive exponent. So what we're going to do is we're going to send x squared on the numerator. Now this is a fine looking answer. If you want to simplify this, in radical form, you can write this as square root of k, because that's what raising something to the 1/2 power is, times x squared, divided by what is m to the 1/3 power. That is really cube root of m. And for me, both are fine. If you give me left, you get full credit. If you give me the right one, they are both fine, okay? All right, but just make sure that m is the only one in the bottom and k and x are both on top, because m was the only one with the negative sign. That's the only one that's going to get divided. All right, 14 is going backward. We're going to have we have a single log. We're going to separate this and write this as long as we can. We're expanding this log. So let's go ahead and, it's kind of tricky. I'm going to go ahead and do some work before I separate these though. I'm going to rewrite this as log of, take a look at what I'm doing real quick, x to the 6th power times y is getting raised to the what exponent? 1/3 power. And z, I'm going to say z to the 1st power, because that's what that's what z is. That's z to the 1st power. And w to the what power? 1/2 power. Let me do that, okay? Because what you will notice is this. Not the denominators. Denominator guys are just fine. They're separated. But you see how they are together? They're together. And outside they have a power of 1/3. So what I'm going to have to do is stick in 1 next to the y, because it's really y to the 1st power. I will have to multiply this outside power to the inside power. So take a look. This is using the exponent rule. I have to do 6 raised to the x raised to the 6 times 1/3 times y raised to the 1 times 1/3. You see what just happened? I multiply this outside exponent to this inside exponent. But do I have to multiply this 1/3 to the denominator? No, because those guys were the only ones. The ones on the numerators were the only ones in the cube root. So I'm not going to multiply 1/3 to the bottom. It just stays as z to the 1st times w to the 1/2. All right, let me simplify this. So this is going to be log of x squared w to the 1/3 z to the 1st w to the 1/2. I think I said w twice. There's no w twice. X squared y to the 1/3 z to the 1st power times w to the 1/2. All right, looking good. Now let us separate this into a single line, okay? So I will have log of x squared plus log of x to the 1/3. But listen, these two are the ones on top. The other ones, as we are going to the bottom, they better have what sign underneath? What sign here? Minus. Minus log z to the 1st minus log w to the 1/2 power. Now this is really, really good, but simplify each term as much as possible. And what they usually mean is they want you to bring down these exponents. Now, bring that 2 to the front, bring that 1/3 to the front. Well, there's 1 there, so you don't have to bring anything down there. So your final answer should be this. 2 times log of x plus 1/3 times log of x minus log of z, minus 1/2 times log w. So that's how you will expand this logarithm using as a sum or difference of logarithms, and do bring down those powers as coefficients in front of them, okay? So that's it for number 14. Let's go over number 15 and 16. Slightly different type of problems. Use log base b2 is approximately 0.327 and log base b of 3 is 0.621. Oh, wow, okay, they're giving us 3 different numbers. But, here's the good news, though. Let me just try to do 3 different colors. Now, they are all common log base, right? Log base b, 2, 3, and 5, and they're giving us some decimals. They want you to approximate the value of the given logarithm to 3 decimal places. Assume b is greater than 0 and b is not equal to 1. Why do they have to give you that assumption? Because, well, that's the base of an exponential function, right? That needs to be greater than 0 and cannot be equal to 1 by definition. So you can ignore that last part if that's confusing you. But let's see. How can we make 75? That's the question. Now look at the ingredients you have. What you want to make is 75 using 2, 3, and what? 5. So using 2, 3, and 5, now I haven't really worked this out yet. So let's think about it together. How can I make 2, 3? So what if you try simple adding? 2 plus 3 plus 5. Is that going to be 75? That's not 75. So what we are doing is it's like a little puzzle. We're going to do something so that we get 75. We're changing the arguments, okay? So what can I do? I can do 2 to the... Now, 75, isn't that 3/4? That's 3/4, right? And quarter is 25. So I may be able to make that by doing 3 times 2, right? 3 times, what am I saying? 5 squared times 3. 5 squared is 25. And if I multiply that by 3, wouldn't I get 75? So you know what? I had to think about it a little bit. Just using the numbers that were given to me, 3, 5, and 2, I can get that, right? I mean, there's got to be another way to do this. There's got to be another way to make 75 using 2, 3, and 5. But this is one way that I saw. So what I'm going to do is I'm going to rewrite my log expression. Log base b, 75, as this, okay? I'm going to separate these into separate logs. I can separate this as log base b of 5 squared plus log base b of 3. Now see if that makes sense. First of all, maybe I can just keep it as 25 for you right now. If you are combining common base log and they have a plus sign in between them, what do you do with the arguments? You multiply them. So if you multiply this number 25 and 3, you get what number? 75. So I'm breaking this 75 into smaller pieces. And why do I want to go to smaller pieces? Because I know what these smaller pieces are. Okay, so I'm rewriting this 75 as the smaller pieces that I know of. Okay, the next one, I'm going to go ahead and rewrite this log base b of 25 as 5 squared. And guess what? I know what this is. Didn't they tell you that log base b of 3 is 0.621? They did, right there. So I just wrote it down. Now next, what can I do? Now take a look. This has a 2 in front of it, so I can bring this 2 down. This is 2 times log base b of 5 and plus 0. That decimal that's just waiting for us equals. Now take a look at this part for me. What is log base b 5? They also gave that to you, didn't they? It's that one. So we're really doing 2 times 0.778 plus 0.621. Now that's going to be our approximate answer, the approximated value of this. So let me go ahead and type this into my calculator. And this is very fun because you have to think about what kind of operation and number, what combination will give you this bigger number 75. So you're thinking backward, really, using the log properties that you know. So approximately, it's going to be 2.177 when you type in 2 times 0.778 plus 0.621. And we have no idea what b is. But we still will be able to approximate what log base b of 75 using the 3 little pieces they gave us. Let's try another one. Now, here's the thing, though. Is this the only way of doing this? Is this the only way of creating 75? I bet not, right? There's probably another way to create 75 instead of using this method. So if you think of another method, if you would like to share that with me, just let me know, okay? Because I love to know more than one way of doing this. Alrighty, because technically, I really didn't use the yellow highlighted log base b of 2. Okay. Alright, let's look at another one, number 16. Log base c of 2, alright, let me highlight this one in yellow, is this decimal. And another one they're giving us is log base b of 5 is equal to that decimal. And then the last one they're giving us is log base b of 7. So what I'm doing is I'm using 2, 5, and 7. And what are we creating? We're creating 35. So think real hard. How can you make 35 using 2, 5, and 7? Oh, isn't 5 times 7 35. And if you divide that by 2, wouldn't that be 35 over 2? So using the 3 pieces, and the 3 pieces are the 7 from the third one, and I also have the 2 from the first piece, and then the 5 was the middle piece. I can use these 3 given pieces and make the argument of the one that we're trying to break down. So let's go ahead and rewrite this, okay? So log base b of 35 over 2 is equal to log base b of 35 minus log base 2, isn't it? Right? I'm going backward. I'm expanding this because a quotient argument can be separated into, I forgot my little b here, 2 separate logs with the same base, connected by a minus sign. And then I can go ahead and rewrite this as log base b of, let's break down 35. 35 is 5 times 7, isn't it? So I can separate log base b 35 as log b 5 plus log b 7 and just bring down your log b 2 there. Now we got everything. Now let's go ahead and write down the decimals they gave us. Log base b 5 was 0.832. Log base b of 7 is 0.997. And subtract the last one, log base b of 2. They gave that to us as 0.4345. So add them and subtract. 0.832 plus 0.997 minus 0.345. And that comes out to be 1.484. I really wanted to give you something different just because. Now, there are a lot of online calculators that will just let you type in and get away with the answer without really you trying it yourself. But these are important properties that I really want you to review. So number 15 and 16, please try them on your exam. They are a little different than what we were doing, but you know all the properties and you know how to break down a number. So you can do this. So that was it for the third video. I have about 5 more left. I got 17, 18, 19, 20, and 21. And I will be back to record those videos.